Okay, so we're going to look at the solutions to the powers section of the quiz review. So the basic idea with the powers is that we recognize that something like this actually means this. So when we're showing that, I think the question says, show why 2 to the 4th times 2 cubed is equal to 2 to the 7th. We want to expand it like this. So 2 to the 4th, multiply 2 times 2 times 2 times 2, 4 times, and then times 2 cubed, another 3 times. Altogether, that's 2 times itself 7 times. So that's how we show that 2 to the 4th times 2 cubed is equal to 2 to the 7th. So we're basically counting up the number of 2's. The next question is similar. We've got 2 to the 8th over 2 to the 5th. So we write out our 8 2's here being multiplied together, and we put the 5 2's in the denominator. The next step is we're going to simplify this. So we do that by recognizing that these pairs of 2's that are being crossed out in red, they equal 1. So we can cross these out. They just cancel out because they don't affect the answer. And we're left with 3 2's in the numerator. So we've just proven that this expression is the same as 2 cubed, because this is 2 cubed. 2 times 2 times 2. So for the next couple of questions, we're applying that thinking to determine, I think the question says, express each of these as a single power. So we're given this, and in our mind, we visualize 5 5's here, and 10 5's here, all being multiplied together, just like in our previous one. So we have 5 plus 10. So altogether, we're going to have 15 5's. So now we're writing this as a single power. This is a power. And we used to have 2 powers, and now it's just 1. So we're combining the exponents by visualizing multiplying by a whole lot of 5's. The next question is similar, except instead of a nice friendly number like 5 as our base, we have 2.4 as our base. But it doesn't change anything. We still have 2.4 multiplied by itself 3 times right here. 2.4 times 2.4 times 2.4. It doesn't matter what the base is, as long as we're multiplying 2 powers with the same base. We can think of 3 2.4's here, multiplied by 8 2.4's here. So altogether, we're going to have 11 2.4's multiplied by themselves. So we're thinking of the 3 plus 8 that we had over here. Same with this one. It's just looks a little bit different because of the x's, but the logic is the same. X to the 15th, we imagine 15 x's multiplied together. It could be any numbers. We're just representing it as with a variable x. So it could be a 3, a 5, a -7, does not matter. 15 of them multiplied together. And then the second part here, x cubed, is 3 more. So altogether we have 18 x's being multiplied together, or 15 plus 3. So we've written this that looks fairly complicated as a single power. Next, we have some questions where we have some situations that might be confusing for some people. So the first one is an exponent of 1. So any number with an exponent of 1 means that you just have the number itself. If it was 7 squared, we would know that was 7 times 7. But it's not. It's a 1. So we know it's just 1 7. Hopefully that makes sense. That's why the answer is 7. The next one, 7 to the exponent 0. Now, a common mistake with this is that people think it's 7 times a 0, but it does not mean that. In fact, any number at all, with any base at all, to the exponent 0 is equal 1. And one way to think about this, if we think about 7 squared, we know that 7 times 7. We can sneak an extra little 1 in there. It doesn't change anything. Just 1 times 7 times 7. So think about now having 0 7s being multiplied together here. So we erase those. That's going to be a 0. We have 7 to the 0 equals 1. We're still left with a 1. So it's not equal to 0, and we'll look at that more when we look at negative exponents. So that's something to put in your mind. When you see a little 0 up there, you know it's going to be equal to 1. For number C, we have negative 16 to the exponent 1. So this is just as if we had any other number, like a 3 or a 5 to the exponent 1. It's just going to be one of those numbers by itself. Negative 16 is the answer. Now, you could think that if we did have negative 16 squared, what might that be? Well, if we had negative 16 squared, then we would want to multiply negative 16 times negative 16, which would make a positive. But in this case, there's just one of them, so it's negative 16. Question D involves a decimal number of 1.5 as the base. So we have 1 1.5 times 12 1.5s. So altogether, we have 13 1.5s. The thing to think about this is that when we don't have an exponent here, when there's nothing written, you can imagine that there's like an invisible 1 there. So we have to add 1 plus 12 times that we're putting 1.5 times itself to get 13. In number 12, we're looking at powers of 5. So we're given numbers like this, and we're asked to write them as powers of 5. And you may remember that in class we made these tables where we had a base like 10 or 2 or 3 and different exponents going down, and we worked out what those were. So this might remind you of that, especially for when we get into the negative exponents. So 5 we can just write as 5 to the 1. This is what we were talking about in the last question. 25 is 5 times 5, or 5 squared. 125 is 5 cubed. So remember when we were looking at this in class, we were imagining that we were multiplying by 5 every time we have a higher power. So times 5, times 5. Similarly, when we go down, we can think that we're dividing by 5. Divide by 5, divide by 5. And this connects to the next group of questions. D is asking to write 1 over 5 as a power of 5. Now remember with our chart, as we're dividing by 5, the exponent is going down. So 5 divided by 5 is 1. So we're dividing by 5. We continue going into the negative exponents, and now we're dividing by 5. Now we start to get fractions. So 5 to the negative 1 is 1/5. So it's like we've got a little 5 to the 1 down here. So 1/5 we write as 5 to the negative 1. It's right here in the table. 1 over 25, that's 5 to the negative 2 right here. It's like we have 2 5s in the denominator. It's like 5 to the negative 2, we can also think of that as 1 over 5 times 5. We know that 5 squared is 5 times 5. 5 to the negative 2 is 1 over 5 times 5. So 1 over 25 is 5 to the negative 2. 1 over 125 is this one here. So we're getting smaller and smaller numbers here. We're dividing by 5 each time. They're getting closer and closer to 0 as we add another power, or subtract 1 to make a bigger negative exponent. The last one, G, is we're given 1 over 5 times 5 times 5 times 5. And we know that we have 5 5s in the denominator. We've divided by 5 4 times. oops, I said 5. 4 times, so we write that as 5 to the negative 4. These two are the same. This is a power of 5, and this is what it means. In the last question, we're asked to put all these powers in order from least to greatest. So the first thing I did when I looked at this was I just looked at the ones that had positive exponents, like this one, and this one, this one. And I know that all of these powers are going to be big. 6 times 6 times 6, that's going to be big. 7 times 7 times 7, that's going to be even bigger than that. 3 times 3 times 3 times 3, 6 times, that's going to be big too. So those ones are going to be very large numbers. The second thing I looked at was this one here, negative 128 to the 0. Well, I know that any number, any base at all to the exponent 0 is always going to be 1. So I'm sort of figuring out that this one will probably be in the middle, and then we'll have some big numbers to the right. The small numbers are the ones with the negative exponents. So 7 to the negative 5 is the same as 1 over 7 to the 5th. This is going to be a really big denominator here. So this number is going to be very small. Similarly, this denominator is going to be very big as well. So when the denominator gets big, if I think of something like 1 over 7, 1 over 7 squared, 1 over 7 cubed, my denominator is getting really big as I go along here. I don't even know what 7 times 49 is off the top of my head, but it's going to be very big. So 749. The bigger the power in the denominator, the smaller the fraction, the closer to 0 that it is. Okay, so now that we have looked a little bit at which numbers are really big and really small, now we can compute the actual value of some of these powers. So 6 cubed, I can put that in my calculator and get 216. Look at the big numbers first. This big number here, 7 cubed, 7 times 7 times 7, 3 times 3 times 3 times 3. I can put that in my calculator and come up with these numbers. Now let's look at the small numbers. For the small numbers, the power is in the denominator. So we can calculate this on our calculator, and it turns out to be this. So this fraction, in fact, is 1 out of 16,807. So if you imagine dividing something into 16,807 pieces, this is one of them. So it's very, very small. 14 cubed, we can do that on our calculator. That's 2,744. Similarly, these denominators we can also calculate just by calculating these powers and putting them in the denominator under 1. So as it turns out, we can now see the values of the different numbers. When the denominator is bigger, this number is closer to 0. So it's sort of the opposite from what you might think. This one is actually this one is 78,000, 20,000. So this is the smallest. This one is 20,000. It's the next smallest, the next smallest, the next smallest. So let's consolidate that. So this was the smallest. It's 5 to the, this was the smallest. This was the smallest. So 5 to the negative 7 is the smallest. Next was 12 to the negative 4. That's this one over here. 7 to the negative 5 is next smallest. 14 to the negative 3. Then here's our one with the exponent 0. We know this is just 1. So all of these are less than 1. They're fractions that are less than 1. Now we get into our bigger numbers. 6 cubed is 216. Then 343. Then 729. So that's one way to approach that question.